We're almost into the double digits. When I had the HDMI in, it wasn't purple, was it? Hopefully it's not my adapter. I just got it. I'll test it with my phone on the other side, because I have a lightning to VGA as well, so. Adapter for every situation. All right, let's get started. So, what's new? Not much, not much. We had a deadline pass this morning for last unit's questions, so hopefully you got them in. The current one is still active and live. Still getting emails about the second assignment, which is great. First assignment, I have not finished all of them yet. So it's on my to-do list, but work keeps piling on my lap, and I keep, so I apologize to I think there's like 20 or so that I'm short, so I should just buckle down and just do them. But yeah, I do promise to get them done as soon as I can. Assignment 2, I think, what did they say for the deadline? It was like the last day of March, maybe, or April 1st. So close to the last day of March. If you have any questions about that at all, please feel free to send along an email. I've gotten several times the question, are you allowed to do it alone? And the answer is yes. It doesn't have to be in groups, but you can do it in groups up to 5. And in fact, you can do it in groups greater than 5 if you get in touch with me first. So I just want to put a bit of a cap on that because, yeah, I don't want a group of 50 coming in all at once. The other piece that I wanted to stress too is that every person that's a member of your group has to appear in the video. And that's because in past years, you'd have a bunch of people attached to a video somehow, but they weren't in the video, and it wasn't clear if they did anything. So I don't want people who are not participating getting credit for other people's videos, if that makes sense, right? Anything else? No? We're good? We're in the middle of a unit, so nothing really new on the go. We're talking about water. Our next unit is going to be a unit on cannabis. So it's a nice hot topic lately. And yeah, a few things like that. I hope my audio is okay. If not online, throw a shout out there to me and I'll fix it. So last class, we've been talking about water, and we talked about several issues related to water. We talked about how water coming into your house can be hard water and some of the effects that can have, and we talked a bit about the chemistry around that. We talked about the chemistry of water itself in terms of its structure and how it likes to form hydrogen bonds. We talked about what can dissolve in water, what will not dissolve in water. We talked about some of those aspects as well. And we talked about fresh water versus salt water and a few things like that. So we're going to move today, and our discussion is going to kind of switch focus. And our focus today is going to be more on drinking water, what makes drinking water safe, and some issues around that. And in fact, the huge amount of chemistry and engineering that goes into providing safe drinking water for us. This picture that I have right here is a map of the world broken down by the percentage of the population in each of these countries that have access to what we would call safe drinking water. Luckily, here in Canada, we're well over 90%, although there still remains water quality issues in many areas of Canada, particularly on reserves, Indigenous reserves in various parts of the country, and this is a major issue with these places. But for the most part, if you look at North America and Europe, Russia, for example, Australia, the so-called developed countries, typically nearly everybody or most of the population for sure has access to safe drinking water. In fact, it's something we just take for granted. We just assume you turn your tap on, there's going to be water there, and we probably don't put a whole lot of thought into this every day. But there are many parts of the world where a very huge proportion of the population don't have access to safe drinking water, and this is one of the leading causes of disease in many of these countries. A variety of diseases that are caused by limited access or no access to unsafe drinking water. That our processing of water that we do here gets us past that problem. So here's an example. This is a bag of water, a little bag of drinking water, and these were distributed in Haiti in 2010. In January, there was a big earthquake, and it destroyed a lot of necessary infrastructure that was providing the population with access to safe drinking water. And so one thing they did is they took these little bags of water, packed them, and brought them down. This was the Red Cross, I believe, that did this. And it was a stopgap measure for sure until they could get, the infrastructure back online. But what's interesting about this picture is it reads right on the bag what was done to the water to make that water safe to consume. And it's in French here, but that's purified water if you're not a francophone. Not that I'm a francophone, but I do know that much. This is reverse osmosis, which is one method of purifying water that was used. Also, ozone, that should look familiar to you. We've talked about ozone in detail when it's in the atmosphere. So ozonolysis is another method. And the last one, it says ultraviolet. We also talked about ultraviolet quite a bit in our unit on CFCs. So we know what ultraviolet light is, right? It's energy that's it's light that is more energetic than the visible light that we can see with our eyes. And so that was another method that was used to purify the water. Water is put in these bags and then distributed for safe use. We're going to look at these methods and a few other methods of ensuring that we have safe drinking water, but I can begin by saying that none of these methods are applied to the water that you get out of your tap. Okay, these methods are great for small, like a water bottle or a bag of water like you see here, but for a huge deployment like we would see in, if you're setting up your sprinkler on your lawn, that wouldn't be done. So for that water, we have a water treatment process, and I'm going to go through some of the steps in a little bit of detail. Of course, it begins, you need some source of fresh water. It could be a lake, it could be a river, it could be a reservoir, it could be a well. And water is pumped up. This would be, I guess we could call this raw water, water that's directly pulled out of the environment somewhere. And this is pumped out of the water, put through a screen, and this would be just to filter out any kind of, obviously if it's a lake, things like leaves and sticks and bits of debris that you don't want getting into your process here. And the very first step here is flocculating agents. Before I get too far into this, I can also say that another way to get drinking water is through springs. And when you get fresh spring water, and I know my parents used to get this a lot when I was growing up, typically that's not treated in any way at all. It's just taken directly from the environment. And I know that the popular springs people would use to get water where I grew up in Antigonish, people would periodically test the water coming out to make sure it was safe. And every once in a while, there'd be like a shutdown and you couldn't get spring water anymore from certain places. But you could make it safe by running it through this whole process here. So the first step is treating it with something called flocculating agents. And flocculating agents, what they do is they get rid of a problem in water caused by chemical species in the water called colloids. And colloids, you can kind of think of, it's like another state of matter. We have solids, liquids, and gases. Colloids are when you have solid particles dispersed in water. And they're dispersed in a way that is semi-stable, like they'll last like that for a long period of time. So in other words, this would be water that you would look at, and the water appears to be cloudy. Okay, so this would be like, you know, if you had muddy water or just murky, or if there's anything in there that made it not see-through anymore, this would have colloids suspended in the water. And the way colloids look, you know, this is kind of a zoom in of what this might look like, where you see all these individual water molecules with that bent 104.5 degree angle, all kind of in there. And then we have these relatively large particles, these large pieces here that you can see all these little like lines on them, those white lines. Those are trying to indicate that these are coated in negative charges. So these negative charge particles, they don't like to be near each other because negative charges repel each other. So this particle and this particle will keep their distance apart. Okay, they're repelled and they stay that distance with water molecules all in between. And we know the positive ends of water molecules will line up around these and kind of stabilize them. So these big particles are big enough to scatter light. So when you run light through it, it makes the water look cloudy. And these might be safe, they might not be safe, but typically the first process, the first step is to get rid of them. And so what we do is we add something called a flocculating agent, and that's generally something with a positive charge that'll cause these to all clump together. So commonly what's often used is something called aluminum 3+, which is a highly charged positive ion that if you put that in there, you might get like an Al3+, and then you might get another one with all the negative charges clump up to it. Like it kind of causes all those negatively charged colloidal particles to stick together. Here we go, Al3+. This process of clumping these colloidal particles together is called flocculation. So basically, this is a way of clarifying the water. And if anyone here has ever managed a swimming pool where you've had to keep the water clear, because sometimes it'll get murky if you leave it just on its own after a while, it's the exact same process. You buy a chemical, I believe for swimming pools, they call it like a clarifying agent or something like that. Typically what that is a flocculating agent that causes those particles to clump together and then typically sink to the bottom. So as you can see over here, after you add the flocculating agents, there's the flocculator, which just mixes everything together, and then there's the settling tank. So those particles, once they clump up, will settle to the bottom, and you'll have nice clean water on top. This is what it might look like. There's a solution of cloudy water, and this water is cloudy because it contains a lot of algae. And you can add a flocculating agent, and what you can see, it kind of starts to clump together, sinks to the bottom, and now we have this kind of solid, massive crud that falls at the bottom, but the water that's up top is much cleaner than it was before. Certainly visually much more appealing anyway if you're planning on drinking this. Probably wouldn't want to take too big of a chug of the water you see here on the left. So here's just another picture of the same thing. This is like muddy water, and you can actually buy little tablets that do this for you if you are somewhere where you don't have access to like municipal water supplies or commercial bottled water, that you can buy little tablets that'll make water you find out in the environment maybe not too tasty, but at least safe to drink. And one of the things they contain typically is a flocculator, which would cause like muddy puddle water like this to be clarified into something that's at least a little bit more palatable. Typically they also contain something that would kill any microorganisms in the water, so you don't get sick. It would sterilize or sanitize the water. Going back. After the flocculation step, it goes into a filter that contains coal and sand. The sand will filter out any flocculated particles from the previous step. And the coal, the charcoal that's put in there, charcoal itself, you know, it's just pure carbon. The way it's prepared generates all these kind of like fissures that you can see in here, right? All these kind of hairline cracks that go all the way through the solid. And these cracks are actually fantastic for absorbing any nonpolar kind of material. So if you run water across charcoal, anything that's typically an organic compound, like, if there's animal waste or things like that, also if there happens to be chlorine, if it's tap water, that will get effectively absorbed through all these cracks and channels in the charcoal, and that will remove them from the water. So it'll purify the water that way. And you probably have seen these if you ever had a fish tank. Fish tanks have a filter in them, and you see all that black material that's in there? That black material is charcoal, and that's to filter these substances that can build up in the tank because fish are peeing and pooping in the tank, and they build up and they decompose, and put too much food in, that decomposes too. The filter is supposed to collect that. Now, of course, a given amount of charcoal only has so many cracks and fissures, and it can only absorb so much. So what you would need to do is periodically chuck it all out and put fresh charcoal in there. Thankfully, charcoal is cheap, it's easy to produce, easy to make, and there we go. Sometimes it's also called activated carbon. It's the same thing. So what does filtering water through charcoal do? It's a picture of charcoal. There's a YouTube channel, like I'm sure you've done this before, where you find yourself on some YouTube channel randomly, and then like you end up watching videos for like a long time. There's one of them, and I forget the name of the channel, but it's like all about primitive technology. And this was how people used to make charcoal like 2,000 years ago or 3,000 years ago. And he builds this little like tower of pieces of wood, and he coats it in mud and then lights it on fire and then seals it up, and it bakes in there for like a couple days. And I don't know, I found it fascinating how they used to make charcoal this way. But if you have a source of wood, basically what you're trying to do is heat the wood to a high temperature for an extended period of time in the absence of oxygen. So it can't burn, it can't catch on fire. Effectively what happens is it dehydrates, it gets rid of water, but it kind of just bakes in there in an oxygen-free environment. What this does is it traps nonpolars like Cl2 and organic. Doesn't trap all the other things that you see there. What's flocculation? That is when fine suspended particles clump together and sink to the bottom. Chlorination is the next step that happens in municipal water treatment. And the purpose of chlorination is to kill anything that's alive still in the water after the previous steps. And this is probably the most important step of the water purification process, because we don't want to be consuming water that contains pathogens in it, right? Microbes and germs. And this is how all kinds of different illnesses can be spread. Illnesses that we probably don't worry about too much because we're used to having safe water supplies. So the way they do this is they take chlorine gas, Cl2. It's a diatomic molecule, just two atoms of chlorine stuck together. It's a gas at room temperature, and it's kind of yellowish. So this is like a bulb, glass bulb, filled with chlorine gas. It kind of has that yellowish color to it. This is actually like really dangerous if you breathe this stuff in. It's kind of like ozone in that respect, where if you breathe in chlorine gas, it'll do serious damage to your lungs. And it'll similarly damage things that are dissolved in water. So they buy these cylinders full of chlorine gas, and they bubble it into the water, and it dissolves in the water, and if it comes into contact with any microorganisms, bacteria, whatever that's in the water, it'll kill it. More than that, and this is actually why chlorine is so good at this, is chlorine will then remain behind in the water. You'll have residual chlorine after you've killed everything and disinfected it. And that travels with the water as it goes through the distribution system, as it goes through pipes, as it comes out your tap. The water coming out of your tap still has a little bit of chlorine left, which is important because if you purify all the water at the source and then just pump it into a system, it could then pick up bacteria or germs or whatever after it's left the plant. By having residual chlorine in there, then that keeps it safe all the way through. This makes chlorine a better option than something like ozone, because ozone, we know, dissipates, right? You could kill everything with ozone, and then you put it back in the system, and maybe 4 hours later, the ozone's gone, it picks up some contamination somewhere, and then you end up with contaminated water in your home. So that's a big deal with chlorination, is this residual protection that it can provide. It also comes out in your water and can affect the taste. So there's a negative, I guess, there as well. Chlorine was used in World War I as a poison gas. It wasn't used for very long, though, because people realized very quickly that you can use gas masks to filter out chlorine. Guess what's in gas masks to filter out the chlorine? Charcoal. So just like charcoal filtration, it can filter stuff out of water, it can also filter it out of air. So a lot of these gas masks that are used in places like the wars, not the war, wars, is if you can filter air through it, it can remove certain substances from the air and make the air safer to breathe as well. All right, here is an ad. There's a website called bellcraft.com that'll sell you a device that you can put on your tap water, and they say this, from a biological chemist. Putting chlorine in the water supplies is like starting a time bomb. Cancer, heart trouble, premature senility, both mental and physical, I don't know what physical senility is, but are all conditions attributable to chlorine-treated water supplies. It is making us grow old before our time by producing symptoms of aging, such as hardening of the arteries. So this may be familiar now. I bring up little things like this all the time in this course, right? Is there anything to this? Well, the closest there would be to this is the fact that chlorine can do more than just kill microorganisms in the water. It can also do chemical reactions because it's very reactive. It can do chemical reactions with whatever else happens to be in the water. Hopefully, there's not much else in the water because you've already filtered it through the charcoal. But if anything does make it through that process, it could potentially react with chlorine. So this is a slide, actually, that I use in my organic chem class. This is a chemical reaction where if you take substance like methane or natural gas, it will react with chlorine under certain conditions and can make molecules like chloroform. And some of these do have the potential to increase your risk of developing cancer. However, is this a meaningful worry in a water supply treated with chlorine? Well, this is what the World Health Organization believes. Risks to health from DBPs. DBP stands for disinfection byproducts. So these are these other chemicals that you can generate by treating your water with chlorine. It says the risks are extremely small in comparison with inadequate disinfection. Okay, if you get rid of the chlorine altogether in your water supply, you're in for a much bigger pain than you could ever potentially imagine arising from chlorinating your water in the first place. So on the whole, the risk-benefit ratio of chlorinating water, it falls heavily, heavily, heavily on the benefit side. Doesn't mean the risk is zero, right? But if I had to pick, I'll tell you which way I'd go. Now keep in mind too, this is from a commercial website that is trying to sell you a product that would remove chlorine from your drinking water. So take that into account too when you are trying to trust a source like this. I should look this guy up. I've never heard of that name. Maybe he's a real person, I don't know. But chlorine you have to be careful with, because chlorine gas, if you take a large dose of this, then you can have very serious consequences. So this was a situation where there was a clubhouse. Basically, it's a place where there was a pool and things like that, and they used chlorine to disinfect the water. And yeah, if a chlorine gas leak happens, it can be very dangerous to your health. So for that reason, chlorine isn't sold in cylinders for people to use in their own homes. The training and so on that you would need to use chlorine makes it restricted to industrial facilities like a water processing plant. So if you're at home and you want to purify your water like in a swimming pool or a hot tub or something like that, chlorine gas is not your solution. Instead, you want to turn to a chlorine alternative, and two common ones are listed here. One of them is called sodium hypochlorite, which we call bleach. So this one here is bleach. This is a very water-soluble compound because we have Na plus ions, which is +1 charge, and hypochlorite ions, OCl minus. And we know many substances with +1 and -1 ions dissolve well in water. So you buy Javex as a solution in water, and this hypochlorite will act kind of like Cl2, except not quite as aggressive, and it's not, because it has a charge, it likes to stay dissolved in water and doesn't enter the gas phase easily. Okay, so this will do similar work to chlorine, and it'll also do all kinds of chemical reactions. If you pour it on your clothing, of course, it'll bleach it, right? Which is another reason why people buy it. I know people sometimes with wells, on well systems, get their water tested regularly and can shock the well by dumping bleach down the well, which I think makes the water undrinkable for a while until the bleach dissipates. But what shocking does is kills any kind of colony of microorganisms you have down there and then prevents the population from reestablishing. In swimming pools, what's used instead of bleach is something called calcium hypochlorite. Calcium hypochlorite still has the OCl minus, but it has calcium 2 plus. And notice you need 2 of these to counteract the charge of a calcium. And we said last class that if things have charges of +2 or +3 or bigger, they're typically less likely to be water soluble. And so calcium hypochlorite isn't nearly as water soluble as sodium hypochlorite. And so calcium hypochlorite comes in like tablets or pucks. So if you're in a swimming pool or a hot tub, they typically can you can either dump them into the filter basket and they'll stay, they don't dissolve, it'll take like a day or two for them to fully dissolve. Or sometimes you see these little floaty plastic things that hover around the surface of the pool. You can put those calcium hypochlorite pucks in there too, and they'll last for a long time. Those are usually preferred because they don't dissolve right away. There's less of a risk of putting too much in, and they'll kind of slow release. Instead of getting a sudden shock, you get this slow release over a day or a couple of days, and it'll provide protection to the water all the way along. So yeah, it's the same active ingredient. It's just whether you want it in there all at once, which is with the sodium, or whether you want it slowly released, which is the calcium system. They call them chlorine tablets, which is kind of funny because there's no actual chlorine, molecular chlorine, no Cl2 in there, but there is chlorine in the form of hypochlorite, and that's what's doing the action here. Ozone we talked about, as something you can use, and we talked about it way back in the beginning of our ozone CFC chapter. And what we said was that ozone can kill things in water as well, just as effectively as Cl2 and a lot of other things. The problem though is that it's short-lived, right? And doesn't provide that residual protection. So it's not used in a municipal distribution system, for example, because of that purpose. If you have a well and you're purifying it just before you drink it, ozone might be a great choice. And you can buy ozonators and ozone generating machines for purifying water if you're going to use it right away. Or you're not pumping it through a distribution system, in which case you don't really need that residual protection. The nice thing about ozone, though, is that it will decompose. 2 molecules of ozone will decompose to make 3 molecules of oxygen gas. And oxygen gas is not toxic, right? So not toxic, well, I shouldn't say that. That's bad for me to say. Everything is toxic with a certain dose, blah, 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 blah. But we would say that all water has some oxygen dissolved in it from a natural source anyway. So that ozone is kind of traceless. It doesn't leave anything behind when you put it in the water. It disappears into oxygen. So this makes ozone actually perfect for bottled water and that bagged water I showed you, where you can put the ozone in, seal it, and then the ozone will kill everything in there and then decompose and disappear. So what you have is perfectly sealed water that you can be certain doesn't have anything living in it, but it also contains no disinfectant in it. So if you ever breach the seal, then you shouldn't use it again. You know how they always say, on bottled water, you shouldn't refill the bottles? I think a lot of people believe that has something to do with the plastic leaching something. It's nothing to do with that. It's just that if you have an unopened bottle of water, you can trust that it's disinfected, that it's safe, that it's nothing alive in there. And if you refill it, you can't trust it anymore, although it's no different from refilling a cup or a glass or anything else, except that if you put the top on and put it in the fridge and forget about it for 4 weeks, and thinking it's a fresh bottle, you drink it, you could run into potential problems doing that. All right, UV purification. We know UV light will kill things. You can take UVC light, which is the most damaging of the 3 of UVA, B, C, and you can pass that over water to kill things that are living in it as well. This, of course, also does not lead to any residual disinfection ability because the light is instant. Once the light's off, it's gone. And so it's similar to ozone. In fact, it's worse than ozone because at least ozone, you can get residual protection for a few hours. You can actually buy a water bottle that has a UV lamp inside of it. And I don't know why you would need this. Like maybe if you're camping and you have lake water or something like that. I don't know if I'd trust it, but it's maybe better than nothing. I can't imagine the battery power you would need in that as well to power this, unless the idea is you plug it in. But apparently they exist. You can buy systems in your home too that will treat your water with UV light. Distillation is probably one of the most ancient methods of purifying water, and we learned already way back at the beginning of the course that it was the alchemists who taught us how to do this, how to do distillation adequately. Distillation means you have dirty water, like in this case salt water, and what you can do is you can boil it, heat it up to boiling, and it'll evaporate. The vapor can then go through kind of a cooled tube, which we call a condenser, that condenses the water back into a liquid. And what we get here should be purified distilled water, which I said is the best water for your iron or anything else that involves, like your coffee maker. I don't know if it's good to use distilled water in a coffee maker because I don't know how that would taste. Get citric acid and you don't have to worry about it. So you can distill water that way, and what happens is anything that won't evaporate, like salt or other dirt or solids or whatever, remains behind in here, and you should ideally only get purified water out on the other side. The problem with this as a large-scale method to clean water or purify water is this takes an incredible amount of energy. You got to heat the water to boiling, which takes a huge amount of energy, and you also have to put more energy in to cool it. So you have to input energy twice to get this product. And while this might work to get a couple liters for your iron, like how much water do you really go through for a year? You'd never want to use this process to purify your water for like a swimming pool or to run into a municipal distribution system to have people spray on their lawns. There's no way, Makes me think like there's some places where energy is almost limitless, like Iceland, for example. Like in Iceland, obviously it can get cold there in the winter and it can snow. Many of the roads, they don't use snowplows though. They have heaters under the roads that heat the roads to the point where the ice and snow just melts off. And why? It's because they have geothermal energy so available they can just run these pipes of hot steam or whatever close to the roads, and then it makes it's very easy, right? That's not the case for most of the world. So yeah, unfortunately, it's difficult to export that energy from Iceland because they're far away from most places. And energy, converting it from a form that you can readily use it to something that you can store is difficult to do. In fact, it's one of the main challenges in adopting electrical energy right now. Gasoline is fantastic for use in cars because you can harvest it in one place, ship it halfway around the world, and use it somewhere else. Or if you're generating like solar power, that's hard to do. It's doable if you have like an electrical grid, but in a place like Iceland, where it's an island far away from everywhere else that you can't reach with telephone poles, that is a big challenge. This is what these systems look like. I don't know, I've never heard of someone buying this for their home, but if you needed a lot of it, you could get it yourself. I've seen these in labs where labs need distilled water, so you could buy one in that situation. But you can see this is like the condenser part, and yeah, distillation. If you need some, just go buy it. It's cheap. Next method, reverse osmosis. This is one of the methods that was listed on that little bag of water I showed you on the first slide here today. Right, so reverse osmosis, what we do with reverse osmosis is make use of a process that we call osmosis. Osmosis is a process probably everyone learns, I don't know, in like middle school science or high school science, which is it's a passive process where a solvent, like water, will pass across a membrane, typically our cellular membranes, and it wants to go from an area of low dissolved solid concentration or low solute concentration. Solute just means stuff dissolved in water. It wants to go from an area of low concentration to high concentration. So an example of this would be your blood cells. Your blood cells are floating in blood plasma, and they'll remain their size and shape as long as the concentration of salts and proteins and whatever else inside the cell is roughly the same as that outside the cell. If you took cells, though, and put them into pure distilled water, like over here, what'll happen is the water that's surrounding these cells will want to move across the membrane to inside the cell. It wants to balance the concentrations inside and outside the cell. So it'll move in and move in and move in, and it'll build up pressure inside the cell, and eventually cells can actually rupture under these situations. Hypertonic would be the opposite. Hypertonic, if you put it in a really salty solution, water would want to move from the inside of the cell outwards, and the cells will kind of shrivel up. So if you've ever gone swimming in a lake where there were leeches and you brought along a salt shaker, that's what's going on right here. Because leeches on their outsides are membranes that have the inside separated from the outside of the leech, and they're wet. If you pour salt onto a leech, what happens is the water inside the leech wants to travel from the inside of the leech to the outside of the leech, and that'll cause the leech to sort of dry up and shrivel up. And I don't know, that's probably painful for the leech too, so it drops off. But it's one method, besides just pulling them, of getting them off your skin. If you ever go out some night with contacts in, and you find yourself sleeping over at a place that is not your own home, and you don't have your contact solution, and you don't have your little contact, case, what I've seen people do is take like 2 cups of water and just put your contacts in the cups. And if you've ever done that, and put them back in your eyes the next morning, they feel right kind of like, eventually after like half an hour or so, they'll be back to normal. But initially, they feel really bad if you just used water and you didn't use the contact solution. And that's because contact lenses are kind of like cells, where they have a certain concentration on the inside of the material. They're very porous. And if you put them in contact solution, then that maintains the balance inside and outside the contact lens. If you put it in just pure water, water will go into the lens and it'll cause it to swell. And when you put it on your eyes, it kind of just looks kind of hazy, like it kind of doesn't, the prescription might not just be perfect or whatever. But eventually what happens is your tears will reestablish the balance, and it'll take a while, but they will go back to normal. They'll bounce back. Osmosis, yes. This was a poster that was in my grade 6 classroom. So here's an example of osmosis where we have a beaker and we have a membrane that's separating them that we call selectively permeable. Sometimes we say it's partially permeable or semi-permeable. It means some things can cross it, but other things cannot. So if we pick a membrane, like many of the membranes that surround our cells, that let water through but don't let anything else through, you could imagine a situation where you have this beaker split in two, one side very dilute sugar, the other side very concentrated. what will happen is the water will go from the dilute side to the concentrated side until you have this imbalance in height. And what happens is this imbalance will create a pressure which will want to push the water back out the other side. So this imbalance will continue until either the concentration is the same on both sides or the pressure gradient gets high enough that water gets pumped back the same rate it comes through. So this is osmosis. Hot dogs too. If you boil a hot dog too long, it'll split. And that is because the outside coating of the hot dog you can think is a semi-permeable membrane. The inside of the hot dog is very salty. So when you boil it in water, water wants to pass through the membrane to the inside of the hot dog, which causes the hot dog to swell. And it can split open like you see here. Now, I say that, but I don't think that's the only factor here, because they'll also split if you barbecue them. They'll split quicker, though, if you boil them. Or steam them, maybe. Although steam, I guess, is exposing them to water, too. But that's how you know they're done, right? When they split. It's also why we don't have to refrigerate things like honey and jam, because there's such a high concentration of sugar in these two items that when germs, bacteria, whatever, land on them, for the most part, osmosis will draw all the water out of those cells and kill them. So microorganisms have a difficult time establishing themselves on extremely sugary, high solute concentration liquids like honey, which keeps them safe. Reverse osmosis, then, is just osmosis in reverse, as the name suggests. So how does this work? Imagine you have a situation where we have a semi-permeable membrane here, separating two regions. One side we have salty water with a high salt concentration, and the other side we have a pure water. We know regular osmosis means the water wants to travel from the pure side to the other side. It's going to go through the membrane that way until we have this sort of imbalance in the water heights on both sides. But what could happen is if you came over here and applied pressure to the salty side, you could squeeze the water, the pure water, back through the membrane here onto the pure side. And you can get pure water this way. So this is a way we can force, with pressure, osmosis to work in the reverse direction. Okay, we take dirty water, we force it against a semi-permeable membrane. The clean water will pass through the membrane to the other side, and the dirt, the crud, stays behind on the other side. So this is how something like this could work. You could have salt water come in, it's pumped into a container where you have a semi-permeable membrane, and what you do is you allow, I guess you would close this one off and allow pure water to come out the bottom. When the top got salty enough, you could close the bottom, open the top, flush out all the concentrated salt water, close it again, open the bottom, and continue this cycle back and forth. And you can get pure water out from this way using salt water. And I'll say this is far more energy efficient to clean water this way than it is by distillation. It takes way less energy, it's way more economical, and better for the environment if you consider global warming as an issue caused by our energy use. So there's a company in Singapore called NEWater, and what they do is they take, some places have much more limited access to clean water. In fact, I'd say everywhere in the world has much worse access to clean water than Canada does. We have huge reserves of clean water in Canada compared to anywhere else in the world, except, I don't know, maybe like Greenland or some other sparsely populated place. So in Singapore, what they do is they take sewage water. It's water that came out of a sewage treatment plant, and you can kind of tell by the color that it's not exactly pure drinkable water. And they take it and they recycle it using reverse osmosis into bottled water. And it kind of sounds gross that you took sewage water, treated water, and turned it into drinkable water. But if you think about it hard enough, probably all of the water that we are drinking now was at one time came out of an organism one way or another, right? It's passed through, it's recycled, there's a water cycle again and again and again. So don't think about it too hard, but this really is no different from what happens to the water that we have. Although I guess you could argue that every time water evaporates and then comes back down as rain, that's just like distillation. So rainwater is kind of like distilled water, except it brings with it soot particles or, PM or dissolved gases or whatever that's in the atmosphere. Maple syrup is typically done, it's actually done around this time of year, right? And what you do is when the sap starts running in maple trees, you tap the trees and you collect the sap that comes out, the maple sap, and you need to boil off the water. You need to get rid of roughly 90% of the water. So syrup, if you had 10 liters of maple syrup sap, that'll produce about 1 liter of maple syrup at the end of the day. My brother did this. He has property with trees and he tapped them, and to get rid of the water, what he did is he bought a propane burner. If you ever saw like a lobster boil, where they had these big pots of water with a propane burner underneath, he rented one of those from a rental place, and he boiled and boiled and boiled. It took hours to boil down all the sap that he had, and he used, I think, 2 or 3 cylinders of propane to do it. And they're, I don't know, like 40, 50 bucks a shot to fill them. And at the end of the day, he ended up with like 2 liters or something. And he spent, I think, almost $200 on the rental and the gas and everything else. So he's like, it's the most expensive maple syrup he's ever produced in his own life, just because his process is very inefficient. The way they do this commercially now is they use reverse osmosis. They use reverse osmosis to press out, I don't know, like 60% or so of the water. And then they finish it off by boiling because it's much more energy efficient. The thing about reverse osmosis is the first water you're pressing out requires the least energy. As it gets more and more concentrated, it requires more and more energy to press out additional water. So they use this to bring it all the way down. Get at least half the water is removed by reverse osmosis in a commercial operation, and then the rest can be boiled off, which saves a lot of money, saves a lot of energy. And I think the boiling step might also be important for the flavor, right? So you have that as well. All right, so lots of things, lots of ways to purify water. We have lots of methods that we could potentially use. Just need to pick the right method. And of course, consider how much do we need, what's the use of the water, and so on. For most of us, as I said, we have access to safe, clean drinking water where we live from our taps that we take for granted. In fact, a lot of people will complain about drinking tap water because it doesn't taste as good or whatever, maybe as some other source. But the nice thing is that if you're in Canada, in most places in Canada, you have access to the most highly regulated, safest drinking water source there is. We have an engineering professor, Dr. Jenny Rand, whose expertise is in municipal water quality, and she has assured me that the most rigorously regulated drinking water supply in Canada is municipal water. So it's much more tightly regulated than bottled water or any other source of drinking water is. So in terms of safety, it should be, at least on the surface, safer than any other source that you can get. You can buy additional water filtration or water purification systems for your own house if you want to improve the quality of the water that you're drinking. So Brita is a very common brand. There's a lot of other brands just like them. Like I think there's one called NEWater, and I don't know what the other ones are called, but you get the idea. They're typically a cartridge that looks something like this that you can either filter water through, or you can have your tap water run through one of these before you put it into a glass, or you can have bigger systems that go under your sink. Well, remember the ion exchange resin that we talked about back when we were looking at the ion exchange resin we talked about for the water softeners? They're these little beads you can kind of see here, right? They look almost like, I don't know, frog eggs or something. I don't even know if that's what frog eggs look like, but I'm just guessing. Fish eggs, maybe. You see that on, anyway. They're these little beads. This is zoomed in. They're smaller than that in real life. And the outside of these is coated in sodium ions that can come on and off. So what happens when you put water with ions with charges of +2, +3, and so on in it, and you pass it across, it will be absorbed by these and the sodiums come off. So this will, and they advertise this as removing heavy metals like lead, which is Pb2+, cadmium 2+. It would work with calcium, magnesium, iron, copper, cobalt, a whole bunch of different metal ions you could potentially have in your drinking water, which if it's tap water in Canada, shouldn't be an issue anyway, because these are all regulated and monitored and so on, so that they're not at dangerous levels. Sometimes you do find lead though in tap water, and actually if you go around campus and look at multiple water faucets, it'll say, this is for washing your hands only, not for drinking because of lead. And what they do is they test these spots for lead all the time. Because a lot of plumbing, especially in older buildings, uses lead, it's true that the water that came from the source, which was the municipal treatment plant, doesn't contain dangerous levels of lead. It's possible that lead enters the system sometime later on. So lead pipes, are unlikely to be used, but often lead is used to join pipes, to solder them together. And you can pick up little bits of lead, and this is particularly a problem in older buildings where the water is stagnant for long periods of time. So the solution is to run the tap for a while until all the water that's sitting in the pipe for God knows how long gets flushed out and you have fresh water that comes through. Because water can leach lead from pipes like that, but not at a very fast rate. So if you're worried about that, a Brita filter will take care of that, although the Brita filters only last, they say what, every 3 months you need to replace it? I'm pretty bad for that myself, but the reasoning is this ion exchange resin can only really capture so much of this before it gets saturated. Now, I personally don't worry about these ions in my tap water at home, so modern house, this is not really an issue. Most houses now, they use like what they call it, PEX tubing for water lines in the house. They typically don't use the soldered copper lines anymore, or that shouldn't be an issue anymore. That's not all that's in there though. The other thing that's in there is charcoal. Okay, charcoal is also inside these. In fact, if you cut one open, and I have one in my office that I cut in half and you look inside, and you can see two little colored particles. There's little black beads and there's little kind of yellowish white beads. And the white ones are this water filtration, this ion exchange resin, and the black ones are charcoal. The purpose of the charcoal is to filter out, just like in tap water or in municipal plants, organic non-polar compounds. So if your water tastes bad, charcoal is what you want. It'll absorb chlorine and potentially anything else that's in there that's non-polar. So sort of this dual system with these water filters to absorb the organic molecules, the chlorine, which is the charcoal, and then the ion exchange will get rid of metal cations as well. Now these have been criticized from an environmental perspective because they're typically not recyclable. They generate a potential large amount of plastic waste. And are they really necessary? They may make your water taste a little bit better, but they don't really improve the safety of the water. Okay? Unless for whatever reason you have extreme lead concentrations in your water supply. So if you want just the charcoal part, there's a company here, and I generally don't, in fact, I criticize companies a lot in here. I generally don't advocate for them, but this one I'm willing to make an exception for because this is a Nova Scotia company. And I haven't checked this year. Hopefully they're still in business. But they make these little, it's kind of like a tea bag. And it contains granulated active charcoal, so GAC. I might have one here actually. Yes, I do. I have an empty container and a whole lot of granulated active charcoal in my bag. It came open. But anyway, it's a company, I think they're based out of Halifax. and they produce these little, there you go, people online, they can see this maybe, yeah. These little tea bag things, which actually make the water taste better, and you can put one in your water bottle, and apparently one of these tea bag things will filter up to 60 liters of water, and it's kind of like a Brita filter without the ion exchange resin. So it'll remove chlorine, it'll remove any organics that can give your water an off taste, especially maybe in a water bottle. Sometimes water bottles can kind of like give a bit of a plasticky taste and get rid of that as well. But it will not absorb any ions like lead or whatever because it doesn't have that ion exchange resin. And actually, they have an ad on their website with like a spokesmodel, and the spokesmodel took this course. And not only did she take this course, but in this topic, when we were talking about charcoal filters, she was telling me that she grew up in the Ukraine. And in the Ukraine, she said what was very popular, and I have that here as well, is you can buy, I'll hold this up for the online people too, buy these little like blister packs of charcoal tablets. And if you look at the writing, you can tell it's like Cyrillic, you know, the non-English. And what these are is if you go out for a night of drinking, the idea is you take one or two of these tablets beforehand, and the theory anyway is that these absorb toxins or whatever, and they prevent you from getting a hangover the next day. Now, as you can see, all of them are still in their package. I haven't tried these, so I don't have any firsthand experience. I find it kind of hard to believe that they would actually work that way because you don't get hangovers because of toxins in your stomach while you're drinking. It's typically because of metabolism byproducts of alcohol that are in your blood, not in your stomach. But it is definitely very common if somebody overdoses and they end up in the hospital, they'll do something like they'll pump your stomach. And the way they do that is they take a bunch of the powdered charcoal that's in here or in one of these pills, and they force it into your stomach, and that'll do two things. One, it causes you to vomit, so it'll get rid of anything in your stomach. But the other thing is that it'll absorb non-polar materials. So if you consumed, you know, like a bottle of pills, for example, and the pills contain non-polar drugs, that they would be absorbed into the charcoal and prevented then from entering into your bloodstream. So it's kind of like a first line of defense to prevent your body from absorbing any more of an overdose of drugs or something like that. Same thing if you drink too much and you'll get your stomach pumped. That's to cause you to throw up and get rid of any additional alcohol that's in your stomach as to not further increase the blood alcohol concentration that you're experiencing at the time. So charcoal, multiple use, right? You can use it to clean water, you can use it to pump your stomach, you can use it, hypothetically, I guess, to prevent yourself from getting a hangover. And yeah, give it a try. Go to their website, you can check out the video. Why is Cl2 added to drinking water? A, kill microbes, provide residual disinfection. Great. What component of Brita filters will remove heavy metals? Ion exchange resin will remove the heavy metals. The charcoal is in there too, but that's not what it removes. It removes the chlorine and maybe other potential organic molecules that could be in there. Non-polar things. TPP and fluoride, we talked about we didn't talk about fluoride yet, but we talked about TPP quite a bit. Good. One more topic I wanted to cover in today's class regarding drinking water, and this is addition of fluoride, which it kind of hinted at the question before. And this is probably the one thing that is added to our drinking water that is the most controversial. And by controversial, once more, I mean controversial in the public eye, not controversial in the scientific community. Fluoride ions are added to municipal water. It improves dental health. Your teeth are coated in enamel, and enamel is a chemical called hydroxyapatite. And that particular chemical can be broken down by acids, and those acids can be generated by bacteria in your mouth when they consume sugar. By adding fluoride, what you're doing is that hydroxyapatite has little OH groups on them that can react with acids, and that causes them to decay. They'll react with H plus as an acid, and you get these little, it starts to eat away at your enamel. So by reacting it with fluoride, what happens is you replace the OH with F, and it kind of chemically changes the outer coating of your enamel and makes it something that H plus will not react with. So it protects your teeth just on the surface coating against, now of course if you brush your teeth or like just regular wear and tear will wear down that layer very quick, so you kind of need to constantly replenish it with fluoride. So that's why we put it in our drinking water. Every time you drink, it protects your teeth against cavities. How do we add it to water? Fluoride you can't just add on its own. You always have to add a neutral substance. So the simplest way to do that would be something like sodium fluoride, where this would separate into ions. It would dissolve, just like the sodium chloride lattice, crystal lattice we showed last class. It dissolves and you get fluoride in solution, and there you go. Only about 10% of our water is fluoridated that way. The more common thing is to add either fluorosilicic acid or sodium fluorosilicate. Notice I spelled it wrong on this container here. But this is either H2SiF6 or Na2SiF6. And what these things do actually is dissolve in water. They react with water, in fact. So if you get something like Na2SiF6, this will react with water. It'll produce sodium ions. It'll make fluoride ions, and it'll make SiO2. And it'll also make H plus ions. And SiO2 is where the silicon goes. That's another word for sand. So this will react with water, make sand, make fluoride, put some sodium in the water as well. And the sand is a solid. It'll filter down into the bottom. And even if you end up consuming sand, it's not dangerous for us, right? In small amounts. Obviously, you don't want to be eating a bucket of sand. Although even then, how much sand could you eat before you end up in trouble? And before even that came out of my mouth, there's probably a YouTube video where somebody tests that out. Please don't eat sand. Okay, so like most chemicals that we subject ourselves to in our diet or whatever, vitamins, you name it, some can be good. Too much is almost always bad, and too little is bad as well. So Health Canada has figured out, through a variety of reports and science and papers and whatever, that the recommended level is somewhere between 0.5 to 1 milligrams per liter of fluoride in drinking water. Too much more than that, and we start to run into problems. Too much less than that, and it's not going to do its job. Okay? There's actually a maximum allowable concentration in water of 1.5 milligrams per liter. So you can't go above that. And so municipalities have to obey those rules. Now you could end up in an area that has much higher concentrations than that just naturally. Fluoride is naturally in water at varying amounts depending on the geology of the rocks where the water is. So certain places, your well water could have very high amounts of fluoride in there. It makes me wonder, actually, when you consider our evolution, if the local water supplies where people would have drank from during our evolutionary period naturally had fluoride levels in this concentration range. I don't know if that's true or if anyone's looked into it, but that would make sense, that our bodies have adapted to fluoride, natural fluoride concentrations that are in that range. It works out that roughly 50% of Canadians that are drinking water from fluoridated sources or from municipal sources have fluoride added to the water. So about half the regions have fluoride added and half do not. So it's not universal. It's not like chlorine, where chlorine's everywhere. Only half the places even bother doing this. So this is areas in Newfoundland. You can see, is Jasmine here? We can tell, she can tell us where she lives here. But you can see these areas where the red dots are. These are areas that have natural well water fluoride concentrations greater than the maximum allowable amount by Health Canada. And so if you're drinking this water regularly, there are potential issues associated with drinking regularly elevated amounts like that. And we'll talk about what that is. This is just geographically along the world where natural concentrations of fluoride tend to be higher than in other areas. So I guess Nova Scotia, we're pretty safe, but we're the best of everything, right? I always laugh when I go through, what is it, East Hants or West Hants? West Hants. And their like sign when you drive in is West Hants, the best of everything, is like their slogan. And I'm like, really? Like it's great, don't get me wrong, but the best of everything. Here's I guess a propaganda piece against fluoride, saying it's so toxic that it's considered hazardous waste by the EPA. Yeah, okay. Pure concentrated fluoride is definitely not a good idea to expose yourself to. One of the basic lessons of this course, concentration matters, amount matters, and all these sorts of things. This one I find especially funny because they have put a hole in a water main and a funnel, and they're going to pour fluoride in. If anyone knows what the pressure is like in a fluoride, in a water main, these two people will be instantly dead from a super high pressure torrent of water that would shoot out of that hole. They do the same thing in Batman Begins. You ever watch that movie? They break open a water main and pour water in, which kind of bugs me every time because, yeah, these are under extreme pressure. You could never do this. Another example, neurotoxic, causing docile submissive behavior. I think we talked about this in an early class. The conspiracy theory that fluoride in the drinking water is to make us submissive and docile, not to protect our teeth. Conspiracy theory. Again, laundry list of negative side effects. You've seen this before too. The problem with excessive fluoride, and this is probably the major problem with it, is it can cause a problem with your teeth called dental fluorosis, where your teeth become sort of white. They get these like white patchy areas. And in extreme cases, they can kind of go yellow and brown. It's a cosmetic issue. When it's mild, it's a cosmetic issue. I think it can get very severe. But this is something that you can see as it develops. If you have too much fluoride exposure, you can develop this problem of dental fluorosis, which is, as I said, a cosmetic problem. People have done studies to see how much fluoride needs to be in your drinking water before you start to see fluorosis. And remember, 1.5 is the max by Health Canada. Between 0.5 and 1 is the recommended. And this is the prevalence of the population that will get dental fluorosis depending on the fluoride concentrations of the drinking water. So you can see if you're down in the recommended zone, basically nobody's going to get it. And if you increase to maybe like above the max, like maybe around 2 or greater, you start to see some people starting to get it. It becomes kind of a major problem if you go like 2 or 3 times the recommended level. And obviously like almost everyone will get it if you go like way, way, way up there. And there are some places that have fluoride concentrations up there just due to natural concentrations in the water. So this can be a problem, especially if you're on well water. Might be something to look into. Cool. So fluoride, I guess from a scientific perspective, is safe if you do this at the right level. About 10 years ago, there was a big debate in the CBRM, Cape Breton Regional Municipality, whether they should be continuing to add fluoride to the drinking water or not. And just prior to this, a similar debate played out in Calgary, and they elected there to remove the fluoride from the drinking water. So this had a lot of back and forth, a lot of misinformation, a lot of fear, a lot of experts, and a lot of, on both sides, people sort of throwing together whether it was a good idea to add fluoride to the water or not. And there were kind of two issues at play. There was people who were afraid that the fluoride was somehow bad, you know, that we had kind of talked about here in these conspiracy theories, which the scientific evidence just shows that that's not true. The other issue actually is a maybe more arguable issue, which is by putting it in the water supply, you're taking away people's ability to decide to consume it or not. That you can decide to consume all the fluoride you want by brushing your teeth, by getting dental treatments and so on. So is it okay, is your individual right to choose whether it's in your water or not, does that supersede the public benefit? And this is an interesting question because this is the same problem with making vaccines mandatory. Is your right to choose more important than your requirement to safeguard the public health? And it's interesting because we have many things which fall on both sides of that argument. So for example, our flour is all fortified with, you know, folic acid, niacin, all these other things are added to flour, if you buy it, to promote health, public health. Same thing with milk, they add vitamin D. And so many of our products that we buy have this built in. Our drinking water, it's the same thing. People will argue that for people who maybe can't afford regular access to the dentist, or maybe don't have good hygiene habits, and those two are generally people with lower means to, you know, seek out these services and so on. By putting it in the public water supply, you're providing protection to everybody, not just those who are kind of tuned in or willing to or able to afford it. What's interesting though, this is a CBC article about this, and CBC is interesting because they have, like most places, an ability to leave comments. And if you go on there, you can upvote or downvote the comments, which is, you know, lots of places have this. But rather than giving you just the sum, they tell you how many upvotes it got and how many downvotes it got. And it's interesting on a public issue like this to read the comments because it gives you a taste, a sense of what the average public, Joe Public, thinks about the issue after reading the article. Maybe not the average member of the public, the average commenter on a CBC article, right? Which is maybe not reflective of the wider population. So for that particular article, the first comment was, why can't water just be water? Which I interpret to mean, don't put anything in it. We just want water. We know why it just can't be water, because it won't just be water for long. You'll have germs, so you need to put chlorine in there and so on. But that has a plus 51 rating with 61 thumbs up and 10 thumbs down. So the majority of the people reading this article agrees with this comment. Next, why add fluoride to water considering every 6 months you go to the dentist, you end up with the awful fluoride mouthwash treatment? So this is sort of appealing to, you know, the idea that fluoride is gross, don't put it in my water. And that, a little bit more balanced maybe, but definitely more thumbs up than thumbs down. Apparently the annual flu shot has general utility. Instead of the long lineups, why not introduce it into the water system? Besides the fact that you can't give flu shots through a water system. Why don't they put a little water come Christmas time? Point is, if people want to ingest fluoride, let them put it at the end of their toothbrushes and swallow away. Fluoride is a chemical. Of course it is. In which case, the fluoridation of drinking water gives municipal governments more power over you than your family doctor. At least doctors can't order you to take chemical substances into your body. So this is that argument that I just stated. This argument that I have the right to control down to the molecular level what I consume, and that right supersedes any potential public health benefit that comes out of there. And that's an argument that many people make. And you see that played out in many different spheres, like down in the States, you hear this a lot around gun rights, that my individual right to own a gun supersedes the public benefit of not having guns in our population, right? That was wildly popular, by the way, 35 up, 9 down. Here's my favorite comment. It's all about quantity. Too little, fluoride, your teeth rot. Too much, it's toxic. Oxygen, water, salt, everything are the same. You need just the right amount. No one takes no fluoride in at all. It's impossible to avoid. All natural water supplies have some fluoride. And by the way, oxygen, water, and salt are all as much chemicals as fluoride. Good luck trying to live without them. That was an unpopular comment. 32 thumbs down and 22 thumbs up, which makes me cringe a little bit. Or maybe like it keeps me in a job because people need to learn that this comment is exactly correct, right? It is all about amount. But the problem is that the average person, they don't like to think about nuance in a issue or debate like this. They want chemical good or chemical bad. They want to put it in one of those two camps. They don't want to consider things like route of exposure, concentration, all these other factors that I keep going over and over again in this particular course. Here's another one. This one goes really hard on the public health benefit side of it. You can read this later if you want. I'm not going to go through the whole thing. But again, an unpopular negative 26 rating for what is advocating really here for the public health benefit side of this argument, which was unpopular. We should get rid of iodine and salt. Iodine is a poison, right? So we do add iodide. It says iodized on table salt, and that protects us from developing goiters. If you don't know what a goiter is, don't Google it. Or you can Google it, but don't Google image it. Vitamin D in milk, et cetera, et cetera. So that, I mean, not many people rang in on that one, but overall negative as well. So here's a professional opinion. Dr. Lynn Tompkins, who's the president of the Ontario Dental Association, or at least she was back in 2011, says that we know it's safe and effective, reaches all populations, prevents tooth decay. They are very much in favor of community water fluoridation. There's a tremendous body of scientific evidence that shows that in the right amount, it is safe and effective. There's over 90 national and international organizations, such as the WHO, that agree that it's safe and effective. Everyone benefits from it, et cetera, et cetera. So at least from the CBC commenting public, and the reason why I say maybe that's not necessarily representative is sometimes you get organized groups of people who might go in and as a group kind of bomb the comments. You see this from time to time. It's hard to say what was going on here. At the end of the day, though, they voted to keep it in. So despite the fact that it wasn't popular with everybody, if you live in Cape Breton, there's still fluoride in your water. By the way, when they first introduced fluoridation into public water systems, it caused an immediate like 40% drop in the rates of cavities. And after they removed it from the water in Calgary, who previously had the same cavity rates in children as Edmonton, all of a sudden after they dropped it, it was like that, right? So I guess one argument to be made against fluoride is that most of the studies that have been done on the efficacy of fluoride in reducing cavities were done back in like the 50s and 60s when fluoride from other sources like toothpaste and dental treatments was not widespread. So the question is, now that we have toothpaste and mouthwash and whatever else, is it as necessary still or still as effective as it used to be? And I guess the answer to that is depends how good people are with their dental hygiene. Why are we adding this to our drinking water? To promote dental health. None of the other things there. Okay, that is where I'm going to finish things off for today because I have 3 minutes left anyway. We have one little piece left in this topic, and it's around bottled water. Hopefully you find this illuminating and exciting. And after next class, we will move on to the following topic. So I think the topic's coming up. We have one on cannabis next. After cannabis, I believe, is like plastics, and issues around plastics. We have a few other ones depending on time. Like we have one on pesticides. There's one on food chemistry. I don't know. We can deal with those when we get to them. Those ones I think are a little bit shorter individually. This one is maybe, I don't know if it's too long, but it's a longer one. 3 lectures. Anyway, it's good stuff, I think. All right, so thanks everybody. And we will see you all next Tuesday.